He's going to fall over. He's fallen over.
It's a greasy pitch. That's no excuse. He's
This is
over.
how far
He's
we are.
on the floor. He's standing up. He's up again. He's down.
Just think of his family back home. Surely now.
Oh! Okay. Quite far. A little bit more seriously, what is real AI? Like the previous lecture, the real AI is what Turing had in mind in the 50s. It's formalized by the Turing test. I think the Turing test is a little bit strange. It's a good start, but it's a bit strange because if the computer needs to be like a person, it also should be stupid like a person. Because let's say person C will ask to multiply two very big numbers, the computer should inject artificial mistakes. So besides this weird stuff, I think this is a good measure of intelligence. And because it's a JBC event, I had to have at least one brain image. And this is a real human brain. And I have two fun facts about the human brain. It's 60% fat, and it's the only object that actually solved the thing that we are all here for. So it's pretty amazing. And I'm from LSEC, which is the Center for Computational Neuroscience. And there we treat the brain as a mathematical function. Just get an input from the senses, and doing some magic computation, which we are interested in, and the output is the behavior of the system. So if this is the case, if we see the brain as such, so we can say that a machine is intelligent if for every task with input X to the system, the machine gives at least as good a response as a human. For example, you would expect the machine to, if I imagine the general AI as better than in physics than Einstein, and better than Freud in psychology, and better than the best human at everything, like in driving, everything. This is the Turing test that I have in mind. And actually, we have it in theory. This object, it's called one hidden layer neural network. It's a mathematical construct, like it's inspired by the brain. And what it is, it's called neural network because it's made of small units that are connected to each other. That's it. And the one hidden layer neural network is a network that have an input X, which is a bunch of numbers that, for example, your X is the sensory experience that you're having. A bunch of number of Y, which is the output that you're producing, like the muscle activations that you have. And age is the brain, it's the memory, it's the thinking. So the one hidden layer neural network has only one hidden layer. Okay, in deep learning we have more. This is the only difference. But the crazy fact about this kind of neural network is that this is the first time I heard about it, it blew my mind. This is actually the reason I get into this field. It's a mathematical fact that said that every function that you can think of, every function, including your brains, every one of you, can be expressed with this simple thing. Just 3 layers of very simple neurons can represent each and every one of you. So you say, okay, so let's end here. We have AI. No, but the problem with theory is that it's not working in practice. So this is this is telling us just that we can express U. But it doesn't say how many H neurons we are going to need, which is usually very, very big number of H neurons. And it doesn't say how we find the weights, W1 and W2, for that will, the weight is actually what is changes in your brain and in this model. So it doesn't give us any prescription of how to get there, just that we can. So, why I'm showing you this is that this talk is going to focus on models that are deep networks, which is similar to this kind of network, but just with multiple H layers. And I'm going to ask in this lecture, does this models are doing some kind of memorization? I should have said before that the reason it's trivial, this mathematical fact, the reason it's trivial is because you can imagine that for every pair of X and Y that you have, for every task, you can have one H neuron, and that way you can memorize everything to infinity. And this is not really interesting. So I'm going to ask the question if this deep neural network, which are the big thing today in AI, are doing something similar to brute force memorization, or they're doing something more like a generalization, like human generalization that we want. Okay, so this is, let's start with chess, which is considered the pinnacle of human intelligence on strategic thinking. At least was in the 90s. But then IBM came and they sort of crushed Garry Kasparov eventually, and today we have computers that no human can come close. And these machines used to work by having a very long sequence of handcrafted rules from experts, from chess experts. And also, they had a tree search to roll out the future of the game in order to find the best move. But today what we have is something else. So today what we have, this is a model called AlphaZero. It's from DeepMind, Google's DeepMind. And this is doing different things. It's learning its own rules. It's playing against itself a lot of times, and with the neural network, with the deep neural network. And it figures out its own rules, and it's winning the game. So actually, to see if this is a brute force solution, or a memorization solution, or a generalizing solution, what I did is I calculated the number of games that this AlphaZero should play until it reaches human level. So it turns out each step here is 50. AlphaZero needs 50 times 120K. It's 6 million games to reach top human play. Just to put it in perspective, if humans would have to play it, it's 1,400 games each day for 12 years without rest. So humans are much, much more efficient learners. And in addition to the brute force learning that AlphaZero is doing, it's also relying on a very brute force search, like hundreds of thousands of positions per second. So AlphaZero, so you might say, okay, what's the problem with brute force? Okay, brute force, as long as it's better than human, we're fine. Okay, the problem with brute force is that is something that it's not going to scale to the problems of the real world. In chess, we have something that's called branching factor in chess that on everything. That it's the number of options that you have to choose at each position, and in chess it's something like 35 on average. And in this number, we can solve with pure brute force, and IBM did this in the 90s. But Go, which AlphaZero also surpassed humans, it wasn't so easy for a long time. So only brute force wasn't enough, but the brute force should have been more sophisticated with learning and stuff. But still, relative to humans, you saw, this is still brute force, learning and search. Okay, so what I'm saying is that for the real world, it's not going to work, because brute force in the real world, no, because you have now infinite options of action that you can choose from. You can just stand up and start dancing and do other silly things. You can do whatever you want. You can just go. And we can't really do a simulation of all the possible, like in the chess and Go. So this kind of brute force will not scale to the real world. This is what I'm saying. Okay, so this is about AlphaZero and chess. Let's move to computer vision, which is actually the most prominent successes of deep learning was on computer vision. This is called the ImageNet dataset. It's an object recognition dataset. It's 1,000 object classes, and the task is to say for each image which category is in the image. For example, here you can see that the network correctly said that it's a leopard. And the network has 1.2 million training images to learn from. Okay. So an interesting fact, today we have networks, this AI, that surpassed human performance at this task already. And this is from 2015, so we're doing much better today. So the question is, as there was before, is the solution found by these networks is brute force, memorization, or is it generalizing like human? So the answer is no, it's brute force. And the most famous example of why it's brute force is the case of adversarial examples. You can see here that the network correctly recognized this picture as a panda. Actually, today we know how to produce this kind of perturbation to the image that are very, very indistinguishable to humans, that will turn this image to any other category that we want. For example, this image for the machine, for the best machines that we have, is a gibbon, which is a kind of monkey. So this is just similar to you know when you're learning for an exam and you memorize the material, and then in the test you get a slight deviation for what you memorize and you don't know anything. This is what the networks are doing. This is exactly the reason they are failing. So what we did is we showed that the networks have trouble generalizing to natural image transformations. Let's see this video. You see this is a bear, and the network correctly recognized the ice bear. And a very small change, the network saying is a baboon. Really, really small change. And it's going to be, you're going to see another example. This is a nice bear now, it's okay, correctly recognized. Just one pixel shift, one frame can make a whole difference. This is not generalization. Okay, so this is how it looks like in the paper. This is what we did here is we took an image of a dog, and we just shifted it a little bit vertically. And you see here the prediction of the network, and you see that very small shift can result in a very large change in prediction. So this is obviously not generalizing. And without getting into technicalities, what we found is that the reason for that is that the network is actually generalizing, but only if the image that the network sees is similar to other images from the training set. This is, we call it the comfort zone of the network. And to illustrate this point more clearly, what we did here is, this is the same graph as before. We shift this image like this, the object, and we see what the prediction of the network, without noise, and here I'm adding noise, but without noise, you see that the network perfectly generalizing. It's not changing much the prediction after following a translation, a shift. But when we add noise, we take the network out of the comfort zone, you will see that it's not the expected thing that the confidence will be uniformly decreasing. What happened is that in some places in space, the network recognizes it correctly, and in some other places, it's not. And it's outside of the comfort zone, there is no generalization for this simple property of shift invariance that you need. So yeah. Okay, so this is a form of interpolation, what you see here, or local generalization. Like what we don't know how to do yet is something that is more similar to extrapolation, to generalize to things that we didn't see explicitly in the training set. Like, we do it all the time. We transfer knowledge from one domain to another, and we generalize much better than these machines, which are pretty rigid. Just a second. Okay, so what I wanted to say more about this. Okay, so maybe I'll end with a very cute example that I found recently, that I made recently. Okay, this is back to chess. Okay, white to move. What do you think? White wins, black wins, or it's a draw? I'll give you some seconds. Any brave souls? What black? Black wins? You just draw. Why is it draw? What is? Okay, go on. Okay, so okay. Let's start with what the machine says. Everyone says white. If you said white, you're in good company. The machine also said white. The best chess engines today, also, the old school engines like called Stockfish, said that it's overwhelming advantage for white. And also the AlphaZero style also said that it's an advantage for white. And I think the reason is that when you're doing brute force search in a tree, you always get, all the position you get to are position that white is up in material, have more pieces. So it doesn't have the understanding that we have, the extrapolation to different inputs than the training set. Like this position, it's never occurred in any chess board in history, I think. So, and every reasonably good human player will know that this is a forced draw. This is a forced draw because the black king is on black, and it can stay there. And white has only white squared bishop. And that's why you can't do mate with the king. So no matter how many light square bishop you have, you can't do a checkmate. So the strategy for black is just keep the king there, nobody can touch it, and do back and forth with the dark square bishop. And the networks, the best networks that we have don't understand it. This is the difference between us and the machines, the understanding, these abstract concepts. Okay, I think I will stop here. Thank you.
Questions, anyone? Question? Yeah?
If you practice the network with noise, it doesn't have an influence about how noise can it get? Like
You mean to train the network with noisy images?
Yeah, for example.
People are trying that. This is always, you can always add something to the training, but then there is something else. It's, I think there needs to be a major change. This feed-forward, memorization, it's not the right solution, I think.
I wonder, because from my opinion, thank you. I just wanted to ask because, from my opinion, it's a bit humanized that if you give the computer a picture and then you start noising it, he will less recognize it like a humans. That if you give him a less clear picture, so he will recognize less or worse than the clear picture. So I just wanted to ask, what's so weird about it that when you give the computer a noisy picture, the accuracy is going down?
What I showed is not that the accuracy went down, is that it failed to generalize to very basic property of shifts of the object. So if you are right, if the confidence of the network were to drop uniformly, this is completely expected. But this is not what happens.
It's about the difference.
It's about the changes, yeah.
It doesn't have to be deep networks, of course.
Yeah, I didn't say it's not possible. I say it's not. We are not close.
We are not there. Okay.
We are not close.
Okay, let them some years of evolution.
Yeah, we need some new ideas or something. I don't think it's a evolution, like more compute, more. I don't think it's that. There are, but it's not like clear-cut evidence for success of this new idea. It's people testing different stuff. Yeah, it's actually a good time to be in the field.